Okay, we're ready. I do, but they're extremely heavy. All right, we're ready to start. We're on the air. So let's see, where are we? It's Wednesday, and we have been talking about generalized Newtonian fluids, and we're basically done talking about them. So let me just summarize here what we had talked about. So we developed this generalized Newtonian fluid. Generalized Newtonian fluid, GNF, is the stress tensor is equal to minus some viscosity function times the rate of deformation tensor. There are a variety of these viscosity functions, so sometimes we write this as eta of gamma dot, where gamma dot is not the shear rate. Gamma dot is the magnitude of the rate of deformation tensor. So that there are some things like that that happen in rheology with nomenclature that are a little bit off-putting, perhaps. So for instance, in this generalized Newtonian fluid, this viscosity function appears. And yet I keep emphasizing that this constitutive equation is good for all flows, not just for shear flow, which is where viscosity is defined. This is going to keep happening. It's going to keep happening that very specific material functions show up in our constitutive equations. And what that means is that we put these things in there because it's a reminder to us what that position in the equation does. And in this equation, whatever is in front of the gamma dot turns out to be the function that's predicted in shear flow. It doesn't tell us automatically what's predicted in elongation or in startup or in step strain or any of those other flows, just the one where that particular symbol appears. So we're going to see, in fact, soon a constitutive equation where the modulus, the linear viscoelastic modulus G appears. And the only reason that appears is because it shows up in the form of the equation in kind of a convenient way. So this is our generalized Newtonian fluid. And once we have such a constitutive equation, we can do, as I indicate on these slides, a variety of things. Most importantly, we can predict material functions. So material functions are all of those functions like viscosity, eta plus, eta bar, elongational properties, G prime, G double prime. Those are all material functions. And those are things we can predict whenever we have a constitutive equation. And the other thing we can do is actually solve flow problems. Solving flow problems means calculating velocity and stress fields. And you're doing that on the homework, and we did some of those in class. So that's what this this group of slides has in it. It has the flow problems that we did. We did pressure-driven flow in a tube. And it follows the same pattern as in Newtonian fluids. You start with the continuity equation, then the equation of motion, and then in order to simplify the equation of motion, you need the constitutive equation. And so it's this equation, the stress as a function of the velocity field, that links the momentum balance to stress. So the momentum balance, rho dv dt plus v dot del v equals minus grad p minus del dot tau plus rho g. This is the momentum balance, but it's not a differential equation only in velocity. It's a differential equation in velocity and stress. Once we have a constitutive equation, though, in principle, we can plug it in, and now this is just velocities, right? Del v plus del v transpose. It turns the momentum balance into an equation that's only an equation in velocity, and then you solve it. Okay, so that's what we did. Now, as you know, it gets a little complicated to do the solution, but the principle is mass is conserved, momentum is conserved, and our usual form of the momentum balance also needs closure. It needs an equation that relates stress and velocity. So we did some examples of that. We did this pressure-driven flow in a tube, and the results are this is the result, which you got in the homework as well. And this is the sketch of the result, the velocity field at any z position. It's independent of z, but as a function of radial position. And then parametrically as a function of the parameter of the model. This is for the particular power law model, which is m gamma dot to the n minus 1. Again, gamma dot is not the shear rate. It's the magnitude of the rate of deformation tensor. In shear flow, it's the shear rate. But in every other flow, you have to know what the flow is. Once you know the flow, you can get gamma dot, and then you can take the magnitude, and that's what it is. So whatever we calculate will be a function of these parameters, the power law index and the consistency index. And so that shows here that the velocity field is a function of the power law index. Where's the constitutive, can't even say the word today, where's m? Okay, there's m. M just affects the overall magnitude of the velocity. So when we plot it as velocity over v average or velocity over v maximum, m doesn't have any effect at all. It's only n that has some interesting effect. Then we also did this drag flow problem, and that was more practice for us. We could do pressure-driven flow between parallel plates. That's one of the few problems probably remaining that I could ask you on a test, frankly, because you can only do really the simplest problems in an examination. But you should be able to do this problem. It may be a long one, but in a testing situation, it would be to do most of it and tell me the boundary conditions. The hard part is really getting those last few boundary conditions all sorted out. So that's the big picture of generalized Newtonian fluids. Doing more calculation would just be to get better at doing those calculations. So you're welcome to do that, and I'll help you if you're interested, but I'm not going to ask you to do more. The choice of the viscosity function eta is up to you. It can be made to fit experimental data to an arbitrary high precision because you can get the steady shear data and you can make up any function you like and stick it in front of gamma dot and you're good. So you can fit it to an arbitrary degree of accuracy. And so that sounds like you can get the constitutive equation to an arbitrary degree of accuracy. But I want to point out to you that that's not the case. And the reason is that there's a flaws or limitations, I should say, limitations inherent in this constitutive equation. For instance, this constitutive equation, no matter what you pick for eta, cannot predict these kind of rod climbing, shear-induced normal stresses. Okay? It cannot do that because in shear flow, okay, so in shear flow, so here's the velocity field, just in general, a unidirectional flow. When we do del V plus del V transpose, there's del V plus del V transpose in general. There's the arbitrary viscosity function. Then we simplify it for only having velocity in the one direction. A whole bunch of things go out. Okay? And we just get that there are these two non-zero terms, and there's absolutely nothing predicted on the diagonal. So no change to eta will solve this problem. Something else it won't predict is to try to get those startup curves better. We worked a little bit on startup curves with my fake constitutive equation. Startup is when you take the shear rate and put it through a step, and we know that the stress comes up slowly and eventually plateaus out. This is pure stress, not eta plus. If it were eta plus, it would go increasing rate this way. This is pure stress. This time-dependent part is not captured by the generalized Newtonian fluids. The generalized Newtonian fluids are instantaneous. Whatever the rate is, the stress is instantaneously tracking it. So it will never say, step it up, but have this slight delay. Okay? Can't do it. And that's because, again, going back to the constitutive equation, this is the stress at time t. This is a function of the magnitude of the tensor. And this is the rate at time t. So if the rate is 0, like in this plot at time less than 0, the stress is 0. if the rate is something, the stress is that something. And so here in the startup experiment, when it steps up to a constant, that means that the stress is going to step up to a constant also. So this slide emphasizes this. The generalized Newtonian models can capture this change in ultimate stress. That's okay. That's the shear thinning part of the viscosity function, is determining what these constant stresses are, and it does that part. It cannot do this part. How about in elongation of flow? Does it do a good job in elongation of flow? Well, here's our friend elongation of flow. And we can put this constitutive equation into elongation of flow. And what we saw from the data was that the steady shear viscosity is 3 times the zero shear viscosity. Well, with the power law model, there is no zero shear viscosity. With the power law model, eta equals m gamma dot to the n minus 1. Log eta versus log shear rate are straight lines with a slope of n minus 1. So there's no zero shear plateau. So the power law model that can't predict Troughton's law. Power law model predicts that if this is the viscosity function, this is the elongational viscosity function, 3 times the viscosity at every shear rate. I haven't proven that, but that's what it picks. If you did, so this is the power law model. If you picked the Kuroya-Suda model, which is the one that on a log plot of viscosity versus shear rate looks like this, okay, this one will also just multiply by 3 and give you eta bar. So it does predict Troughton's law here at low shear rate, and then it predicts stuff that may or may not be true at high. The data we saw showed that even when on polystyrene, either shear rate or elongation rate, what we saw is that when it's a shear thinning fluid, very often it can be a little bit like that. Slightly shear thickening fluid. So this isn't very accurate here. So the power law, the generalized Newtonian models have this mirroring effect where one just mirrors the other. And that's not accurate. So this is my summary of these generalized Newtonian models. They're not garbage. Even though I've pointed out all their shortcomings, they're used. And they're quite useful. When are they useful? They're very good for pressure drop flow rate. So if all you want to know is what pressures might you get in a mold, you can do a mold filling simulation with a power law model. That's okay. They're much simpler to calculate with than anything we're going to talk about from here on. If all you want to do is answer questions about steady shear flow, they're not bad either. So for instance, Julie King works with highly filled, carbon-filled plastic materials, and she's interested in just comparing the processing rheology of those materials. The power law model is perfectly fine for such a thing. Because what do you want that viscosity curve for? Is pressure drop flow rate. So that's going to be fine. The other advantage is that it got us started on non-Newtonian fluids. So now that we're started, we're all lubed up, we're ready to go to something that can do those more sophisticated things. And here are the things we're going to try to track down. We're going to try to track down normal stresses, but I'll tell you, I'm putting that off. First, we're going to track down startup and cessation effects, time-dependent effects. One other disadvantage of the generalized Newtonian fluid model is because we just created this out of thin air. We said, I have a Newtonian model I'm rather fond of. It's wrong because it predicts a constant viscosity. Why don't I make it right by putting a non-constant viscosity in? And so we made this up. Fair enough. It's not that sophisticated logic, but it's perfectly fine, because the idea is you take a guess. We do that all the time in science and engineering. You take a guess, you try it out, and you see what it does for you. So now we've done that. We've taken a guess, we've tried it out, we've seen what it does for us, and now we're going to try to do better. Those were the slides that I didn't have with me on Monday. All right, so here we are with today's new material. Now we're going to address this startup and cessation problem and try to get that right. Right? So we're in the process of guessing constitutive equations. So let me begin by summarizing what always has to be the case for these various constitutive equations. We're looking for stress at a given time. I don't always write that time there, but that is the case. Stress at a given time. And it's going to be a function of the shear rate function. And it can also be a function of various invariants of that shear rate tensor. It's going to have information about the material in it in the form of the parameters like m and n in the power law model. It's got to give us a tensor. It's got to be independent of coordinate system. It's got to be symmetric. This one I'm going to just say it, but I'll talk about it later. It's going to give us some help later when we're looking for those first normal stress differences. It must make predictions that are independent of the observer, since things happen independent of an observer. And it should give us what we actually observe. So the constitutive equations we have thus far are the Newtonian and the power law generalized Newtonian fluid, or the generalized Newtonian fluid in general. And as I pointed out just a second ago, so far the stress at time t depends only on the rate of deformation at time t. So this is more reiteration of what I've been saying. Now we want to try to capture these startup effects in both, well, we're not going to get to the first normal stress difference, but in viscosity. There's the actual data again for your memory. So how are we going to fix this situation? We have a constitutive equation. Let's start with a simple one. Let's say a Newtonian model. I'm going to call the Newtonian parameter eta tilde. And this is a Newtonian model. And it is telling us that the stress at any time is given by the rate at some time. I want to, just to get used to the idea of dealing with different times, I want to change this a little bit and add another term, okay? I'm going to add another term that depends on what the rate of deformation tensor was, let's say 5 seconds ago. Okay? That's all I'm doing. I'm saying that if I have a material and I put it in my flow cell and I start from 0 and I start shearing, then at, let's say this time, 2 seconds later, 1, 1000, 2, 1000, at this time, the stress that I have now depends on what I'm currently doing, which is shearing. But it also depends on the fact that 2 seconds ago I wasn't shearing. Okay? And that way I can build in some of the effects of the startup. As it goes on and on, okay, shearing and shearing and shearing, it can remember, our observation of materials are that they can remember some of what happened to them, but they can't remember everything. So we're also going to build into our model a fading memory, so that at the beginning it can remember that it used to be not moving, but by the time it gets way out here, steady state, it can't remember anymore. And so from here to the rest of infinity, the stress remains constant, and that's how our materials behave. So this little model I'm working on here says there's an instantaneous contribution to the stress, and there's a contribution to the stress from what happened 2 t0 seconds ago. And I'm going to just arbitrarily make this 20% lower than of a contribution than the Newtonian contribution. Okay? So this is a little tester constitutive equation just to see what doing that kind of thing does to the model. So this is fluid memory, but it's also fading. So this is faded fluid memory. And this is a pure Newtonian contribution. If later I want to make it a shear thinning material like a power law fluid, I can just change these eta tildes to m gamma dot to the n minus 1, something like that. So we've made up a model, and now we have to play with it and see what it does. So that's what we'll do. Let's start by calculating the steady shear material functions, which we've done before. Okay? So here's a new constitutive equation with a wrinkle, this dependence on time. Help me predict the steady shear viscosity. Can you start by telling me what psi 1 and psi 2 are? Anybody off the top of your head?
0.
Why?
Because it's not going to predict anything.
Right. It's steady shear flow. And steady shear flow has zeros on the diagonal for all times. So it's never going to predict those again. So those are going to be 0. We could either realize that now or we'll find it out later. Okay, so here's our kinematics. And we actually have done this so many times, maybe you'll remember what del V plus del V transpose is. Okay, it's got just this function, which is a constant in this case, in the 2, 1, and 1, 2 positions. Okay, so gamma dot for this flow is 0. This is the steady version, so I can just put gamma dot naught right in here. And what's important for this calculation is this is gamma dot for all time. Right? This is steady shear flow. So the velocity field is sigma dot x2, but sigma dot, which is in general a function of time, is just equal to this constant. So that makes this calculation very easy to do because now this gamma dot of t and this gamma dot of t minus t prime, they're the same. They're both equal to the same thing. So that means that the stress tensor is equal to minus eta tilde times 0 gamma dot 0 gamma dot 0 0 0 0 0, that tensor, plus 0.8 times the same tensor. Okay, that's the simplest possible case, steady shear flow. So when we add those up, this has a coefficient of 1, that's 1.8. We end up with tau 21 is equal to 1.8 eta tilde gamma dot naught. And therefore, our viscosity, which is defined as minus tau 21 over gamma dot naught, is equal to, I forgot my minus sign, so there's the minus, is equal to 1.8 eta tilde gamma dot naught over gamma dot naught. Eta is equal to 1.8 eta tilde. So for this memory model, adding that second term increased the viscosity. So there are two things contributing to the resistance to flow. One is its instantaneous response, and the other is its memory response. But they don't qualitatively change how the viscosity function looks. It's still a constant. Okay, this is a constant. The fact that it's 1.8, or not is irrelevant. I mean, this relates to this parameter eta tilde, but there's nothing really exciting here. But it gets a little bit more interesting when there's time dependence. Okay? Startup of steady shearing. Okay? So let's try again. Here's our model. Now we're going to do what is eta plus for this flow. Oh, and I didn't double check, but looking back here, you see there's our zeros on the diagonal for psi 1 and psi 2. All right, so now let's ask what is eta plus. Is this the right gamma dot for eta plus? It's not. Okay, for eta plus, we have to do del V plus del V transpose. Del V is going to have sigma dot in it. But this sigma dot is not a constant anymore. It's a function. Right?
Well, that is for t greater than.
Correct. For t greater than 0, that is correct. Okay, so let's be formal about this. You're completely correct, Juan. Right, so let's start with gamma dot in this flow is 0, sigma dot of t, 0, sigma dot of t, 0, 0, 0, 0, 0. And then as Juan pointed out, this, in our case, plugging in what sigma dot is, it's equal to two things. For t less than 0, it's equal to all zeros. And for t greater than or equal to 0, it's equal to 0, gamma dot 0, 0, gamma dot 0, etc. Okay, so sometimes it's nothing, and sometimes it's something, just like with any startup. All right, now, here's the hard part. How do we plug that in to this constitutive equation? At t equals 0, what's the stress? 0, that's right. At t equal 2 seconds, what's the stress? The shear rate at 2 seconds, is there going to be a contribution or nothing?
Constant.
There'll be some, because time is greater than 0, right? So there will be a contribution from this term. At 2 seconds, will there be a contribution from this term?
No.
Why not, Carl?
Well, it depends on how much you're removing the T naught.
Right. It depends on what T naught is. If T naught is 1 second, is there a contribution?
Yes.
Yes, because it's been shearing for 2 seconds, and so 1 second ago it was shearing. If T naught is 5 seconds, no, because 5 seconds ago it wasn't shearing. So there's kind of a subtlety there. It depends on the time. Okay? So let's see if we can sort that out. So for starters, we'll do the easy one. T less than 0, the stress tensor is 0. We got that because both terms are 0. For t greater than 0 but less than T naught, this term contributes. This term doesn't contribute because gamma dot at t minus T naught, if t is less than T naught, this passes 0. So here's our startup function, sigma of t. And when the time I'm interested in is back here, the stress is 0, the stress is 0, the stress is 0, the stress is 0. And that's what we've got here. When we cross the boundary, there's some interval called T naught. And if we're at less than that interval, what I remember is still nothing. and my time is moving forward, and what I remember is still no flow. So in that regime, the stress is equal to this contribution and no contribution here. So it's equal to minus eta tilde times 0 gamma dot 0, 0, gamma dot 0, 0, 0, 0, 0. Now when I let t be greater than t naught, now I'm out here, and I'm remembering this time is something happening. Okay? I'm out here, I'm asking about this time. This is the t naught interval. And here's, this term always contributes. But once I get past t naught, I'm considering a time that when you go t naught seconds ago, the flow is going. This second term contributes again. So for t greater than t naught, the stress is equal to minus eta tilde times that first gamma dot, 0, gamma dot 0, 0. But this second term also contributes, plus 0.8. Actually, there's a minus sign. I'll put the minus sign on the outside. Minus 0.8 eta tilde times the same tensor, 0, gamma dot 0. So because of this second term, first term business, we have a kind of a different function. It says, if I sketch it, stress as a function of time. When t is less than 0, it's 0. If I make this t naught, when t is between 0 and t naught, I get something that jumps up to the level 1 times eta tilde. This is tau 2, 1. When I pass t naught, there are these two terms, and it jumps up to 1.8 times eta tilde. The material elements at these times cannot remember that it was ever at rest. And so it's at full strength. It gives the viscosity that you would get at steady state. But during this little period here, there's some memory that I used to be completely stationary, and the stress is less. So I've got that summarized here. In steady shear, of course, we predict no normal stresses, and the viscosity is at full strength, which is 1.8 eta tilde, where eta tilde is the parameter of my model. And in startup, it steps up in stages from 0 to eta tilde, which is just the instantaneous contribution, to this part, which is the full strength contribution, because it can no longer remember that it was ever not moving. Here's the sketch, and it looks a little bit hopeful, okay? There's some, by adding these memory effects, we're able to kind of ease the curve up into the startup, because we're asking it to remember that it used to be not moving. We haven't got this perfect, but we've got the idea, right? We can make it more perfect. Let's fiddle with it a little bit. What if we add another term? Okay, so here's instantaneous. Here's t naught. Here's something that says I can remember 2 times t naught seconds ago. And maybe you can guess how that would turn out. There's always this instantaneous contribution. That's this one. If it's shearing, there's a stress, the Newtonian contribution. Here's the memory from short time memory, and here's the memory from long time memory. Out here, it's been a long time since it wasn't shearing. So it's only those long time memory effects that are adding up that are subtracting actually from the steady shear response. All right? So you can see it's getting a little smoother. And if we get really obsessive about this, we can keep adding terms. And we want these terms to decrease in importance. So this one was 1, this was 0.8, this was 0.6, as I went backwards in time. So here I'll get a little organized about it. Let me make it an exponentially decaying memory. So here's my times. This is instantaneous. This is T naught, 2 T naught, 3 T naught. We're going backwards in my memory. And I'm going to make the coefficients 1, 0.37, 0.14, 0.05, because those are e to the minus p. It's arbitrary. Just like with the generalized Newtonian fluid model, I can pick what I like. I like the exponential function. It seems like a very common one in physics. There's nothing essential about it. I'm just picking it. And I'll sum this to infinity. And what will I get is a very nice startup function, very smooth, very reminiscent of what's actually measured. Now, the next few slides have some complicated discussion of how to turn this into an integral version. You can either follow it or not. It's not that important. Okay? The bottom line is you know that an infinite sum can often be turned into an integral, and so can this. Right? So if I look at these various terms in the summation and identify them with these area elements, then I can replace this infinite sum with the area under this curve. If I do that, and I said I'm not asking you to follow that in detail, this same summation, remember integrals are sums, here's this same summation of an exponentially decaying function times the rate of deformation at those times in the past. And here's the coefficient eta tilde. This model is a real model, and it's called the Maxwell model. Okay, this is the Maxwell model. It has two parameters in it. It has a parameter that's related to that T naught. How far back can I remember? And that parameter is usually given the symbol lambda, relaxation time. It has the symbol eta naught. Maybe you'll guess that this eta naught will turn out to be what this model predicts in steady shearing at low rates. Okay? But for our purposes, it's also just a parameter of the model, and it relates to the overall magnitude of the stress. It's a constant. So we've actually very quickly developed a second constitutive equation besides the generalized Newtonian fluid, one that has time dependence, and one that we have to now check out and see how it does.
So, is this the same Maxwell from all the other Maxwell versions?
This is the same Maxwell as the Maxwell who did electromagnetism. Yep, James Clerk Maxwell.
You just did it, just like you did it right there? Like he didn't...
He did not do it this way. I'm actually going to show you the way he did it. Maybe I didn't. Yeah, I need the next lecture. Hang on a second. Okay, here we go. This is actually the way. Maxwell derived it. Okay, the Maxwell. Let's see, do I want to predict first? No, I'll do this first. Okay. So the Maxwell model is a model that includes fluid memory. But the way Maxwell derived it was actually in differential equation form. Okay? And perhaps for Carl, because he's a mechanical engineer, this will be a more familiar way to derive it. Because this is related to, this is the way he thought it was a very mechanical analogy of how to arrive at this differential equation. Yeah, actually, it looks like I want to. Oh, I got all the way to the end here. Here we go. This model was derived by Maxwell, and it is the same as the integral one we got, by thinking about fluids in two ways. One is as liquids. So when you have a liquid in between two parallel plates, you know that when you shear it, you get a stress that's proportional to the rate. When you put a solid between two plates and try to shear it, you get a stress that's proportional to strain. Okay, so one is proportional to rate, one is proportional to strain. And we talked about that when we talked about the small amplitude oscillatory shear material functions. So we can actually add mechanical elements that describe rate dependence, which would be a dashpot, and strain dependence, which would be a spring. So I'm going to actually skip a couple of these slides because I don't think I need to go through them and go right to the mechanical model. This is Maxwell's picture. Maxwell said, when I have silly putty, of course he didn't have silly putty, but something that's viscoelastic, there's an effect that's just an instantaneous shearing, and there's a memory. And this reminded him of putting a spring in series with what's called a dashpot. So what's a dashpot? A dashpot is like a shock absorber. And so there's a paddle in here and then the orange Newtonian fluid. And when you pull these plates apart, you're going to stretch the spring, but the spring is going to try to retract. And the retracting spring is going to cause a relative displacement between this outer casing and this paddle. So while that's retracting, it's going to be generating a stress also. And that stress is due to a sort of a Newtonian contribution. So if I pull these things apart, it will pull apart, and then the spring will slowly pull them back together, but they won't come all the way back together because there will be some displacement of the paddle inside the shock absorber. Okay, so this is what Maxwell said. He said there's a viscous contribution and an elastic contribution, and I think a good way to combine them is in series. Now, that's arbitrary as well. You could combine them in parallel. And if you think about it, that would give a different kind of behavior. So for instance, if I had a spring and a dashpot in parallel, if I pulled this down, I'm pulling on the spring all the time, right? If I pull this down, there'll be some amount of stress that will disappear because the dashpot will flow and then stop contributing stress. But there will always be stress from the spring. And so if I let go, it'll spring back. That's not true for the Maxwell element. Okay? If I hold this for a long period of time, this spring will eventually retract all the way. This dashpot will flow, and when you let go, it will not spring back. Okay, so different combinations of springs and dashpots can give different types of viscoelastic response. So this is just Maxwell's idea. I think he essentially hypothesizes that this is how he has seen polymers behave. For instance, silly putty, if you pull on silly putty or bounce it for short times, it acts like it's just a spring, and that's what this would do. If you hit this with a hammer, it would just ring back and forth because the spring would ring back and forth. But if you push on it or pull on it and a long time, it'll flow like silly putty. So what's the equation for the displacement of these plates? The total displacement is the displacement of the spring plus the displacement of the dashpot. And we can combine the force laws for the spring and the dashpot by using that summation equation. So the force law for a dashpot is Newton's law of viscosity. The rate of change of the length with time, that's like the shear rate, is proportional to the force through the viscosity. And the spring constant from freshman physics is force is proportional to displacement. So the displacements have to add. They're hard to add up in this form because this one's a derivative. So we'll take the derivative of this whole equation, time derivative, and then plug in. I can plug in the spring one from the first equation and the dashpot from the second, and I get the total displacement. This, what I did here was the total, I'm calculating the total displacement in terms of the rate of change of the force. That became rate of change because we needed to take the time derivative of this elastic term, and then the force itself, because that comes directly from the time derivative here. And we get this differential equation. So here's the final differential equation. It's a very simple differential equation. And Maxwell said, well, if this is going to give us a constitutive response, force is like stress. Rate of change of force with time is like rate of change of stress with time. And rate of change of distance, total distance, is like deformation. And if I want to further say, I'm not only talking about shear, but all flows, I can just turn everything into a tensor. Tau 2,1 becomes the stress tensor, and gamma dot 2,1 becomes the gamma dot tensor. So I don't know which one gives you a better sense of material behavior. The one with the memory that I did gives you a very explicit knowledge that this final result, which I haven't proved yet is the same, but it is, gives you a very nice memory of it as a material with fluid memory. This one, we can still interrogate it a little bit to find out what it's telling us, but we have to make a little calculation here. So here's our new constitutive equation, the Maxwell model. It has two parameters, g and eta naught. This eta naught over g is also called lambda. And yes, it will turn out to be the same lambda as in our other constitutive equation. And it's called the relaxation time. And we can go back to that picture of this as a combination of viscous and elastic by looking at two limits. Let's start with steady shear. In steady shear flow, all time derivatives are 0. Okay? So if all time derivatives are 0, we get this constitutive equation. What does that constitutive equation give us? You recognize it? That's a Newtonian fluid. Okay, so at steady state, this gives a Newtonian fluid. Right? That's that dash pot. If we're pulling this at a steady rate, this spring just stays at its equilibrium length, and the fluid just flows at a very low rate. Not pulling fast, pulling slowly. Pulling very slowly, it just acts like a Newtonian fluid. The other limit would be at very high rates. Now, at very high deformation rates, the magnitude of the stress is not as important as how fast the stress is changing. This term is really, really big. So when this term is really big, we can neglect the tau term. So we get tau plus lambda d tau dt equals minus eta naught gamma dot naught, and we're going to neglect this term. And I'm going to put this back in as eta naught over g, so I can cancel the eta naughts. And I get d tau dt is equal to g minus g gamma dot naught. If I then integrate it with respect to time, I get that tau is equal to minus g, the integral of gamma dot with respect to t. And this gives the strain tensor. So this equation, tau equals minus g, the strain tensor, this is an elastic solid. So these two limits of the Maxwell model are very slowly shearing. It gives a Newtonian fluid. And bouncing it, really hitting it fast, it just bounces like a rubber ball. Exactly what we saw with silly putty. Okay? At very low, when you sit it on the table and let gravity take over, it flows like a Newtonian fluid. And when you bounce it, it bounces like a rubber ball. Okay? So it's a reasonable model. Next time, I'll show you that it's the same as the other one. And then we have to take it out for a swim. We have to predict material functions and, in principle, solve flow problems with it. Okay? And that's what we'll start off on Friday.